Hello, welcome to another Cosmology Talk. Today we have Indranil Banik, who is a postdoc, and Moritz Haslbauer, who is a PhD student, and they're both at Bonn University. They're talking today about a paper, a model that can potentially resolve the Hubble tension using hot dark matter and MOND, modification of Newtonian dynamics. It ends up with us living somewhat inside a large underdensity, which would be impossible in ΛCDM, but is possible in this model. The model might seem a little exotic, but the longer time goes on with no non-exotic explanation of the Hubble tension, the more we should be considering solutions that do seem exotic. And exotic is obviously also in the eye of the beholder, and nature has surprised us before. We should leave no stone unturned. So, do you guys want to start off by telling us briefly what you did that is described in the paper?
Thank you very much for this nice introduction. And before Indranil and I will give a more detailed presentation of our publication, The KBC Void and Hubble Tension Contradict ΛCDM on a gigaparsec scale, Milgromian dynamics as a possible solution, I will start with a brief summary of our findings. So the universe evolved through expansion and gravitation of matter, which leads to some regions having more galaxies and others having fewer galaxies. And this variation in the matter field directly reflects the way in which gravity has created structures out of the initial density fluctuations over the last 14 billion years. And thus the observed spatial arrangement of galaxies on scales ranging from 100 kiloparsec to a gigaparsec scale is a very powerful test of different cosmological models and gravitational theories. So several surveys covering the entire spectrum made an exciting discovery because we are in a region of the universe containing much fewer galaxies than on average. And in 2013, Keenan-Barger and Cowie found evidence for an incredibly huge local underdensity with the density about 2 times lower than the cosmic mean density and with a radius of 300 megaparsec. And this underdensity we call the Keenan-Barger-Cowie void or just the KBC void. And the results by KBC are striking because the standard model of cosmology predicts very small density fluctuation on these scales. And in our paper, we showed that the formation of such a huge void is not possible in the standard model of cosmology called ΛCDM. And the situation will become even worse when we also include the Hubble tension, because this worsens the problem. Therefore, we decided to study the formation of cosmic structures in Milgromian dynamics. And we showed that due to the enhanced structure formation, voids like the KBC void naturally arise in this framework. And such extended and deep underdensity causes now an interesting effect. So assuming we have an observer close to the center of the void, as indicated by this yellow star in this image, since parts of the universe beyond the void with more galaxies pull galaxies in the void outwards. And this makes the local universe appear to expand faster than it actually is. This situation is illustrated by these red arrows here. And we showed that the high locally measured Hubble constant is just a logical consequence of enhanced structure formation in MOND. And this brings me now to our take-home message. So using the Millennium XXL simulation, we showed that the observed KBC void falsifies ΛCDM at 6.04 sigma. And when we combine this with the Hubble tension, which recently exceeded the 5 sigma threshold, the observed KBC void and Hubble tension falsify ΛCDM at 7.09 sigma. And we showed that both problems do not occur in MOND. And with this, I hand it now over to Indranil.
Hello, everyone. I'm going to start off by briefly explaining the observations that motivated us to do this project. And these are related to the Keenan-Barger-Cowie void. So although it's named after these three people, in fact, there's a lot of additional evidence beyond just their paper. A local underdensity is actually evident across the entire electromagnetic spectrum, from radio to X-rays. So here's some references which are discussed in our article as well. The most important that we were using is this Keenan-Barger-Cowie paper from 2013. What they did is they looked at the 2 micron galaxy catalog, the 2M++ galaxy catalog in the near infrared, and they looked at the luminosity function or the number counts of galaxies in different redshift ranges. And they found the results shown in this graph. So the density relative to some fiducial value and is plotted here as a function of the distance. Now, at distances beyond about 400 megaparsec, the values all go flat around some particular number, which if you divide out by that, you'll get 1. So we assume that this is the cosmic mean density of matter. However, at smaller distances, the values all drop off very substantially, indicating we are in a large underdense region. This light blue point is one of the most important for us because it covers the distance range from 40 to 300 megaparsec, and it covers 90% of the sky. The density inside there is approximately half the mean value here. So the fractional underdensity is 46%, an error bar of 6%. So that's one of the most important observational constraints that we consider. Relating question of whether this is sort of possible in ΛCDM or how it works in different theories. This is what we were trying to find out. For this, we use the Millennium XXL simulation. So this has a box size of approximately the same as the Hubble radius. What we did then is we put observers at 1 million different vantage points on a grid in the simulation. And we looked at the region within 40 to 300 megaparsec of each observer, with 10% of the sky removed to account for obscuration at low galactic latitudes. And we selected subhalos with stellar masses more than 10 billion solar masses. These stellar masses are derived using semi-analytic prescription because this is a dark matter only simulation. So what is done then is we used the total stellar mass in subhalos satisfying this condition in this distance range and in relevant region of sky to work out that the expected root mean square density fluctuations are 3.2%.
When you do that, does the number density of these greater than 1E10 subhalos go to the same number density as the observations at the 400 megaparsec scale? Because that would seem like a good check. I'm just trying to wonder how one knows that these 1E10 solar mass halos are the equivalent thing to what the observations were seeing.
Yes, this is actually a good question. So in ΛCDM, I think some abundance matching kind of prescription is used to assign halos a stellar mass. And that is, the standard assumption regarding how ΛCDM works. It's difficult to do what you are asking directly because that would require a hydrodynamic cosmological simulation like Illustris, which is also sort of much larger than the KBC void. And at the moment, these are not available. However, one important thing to realize, which I was coming on to, is that the density fluctuations we obtain in this way are 3.2%, which you can also derive just on pen and paper using the value of sigma 8 that is given by the Planck CMB observations and using the scaling relation that it declines inversely with the size of the region. So there's no reason to doubt that on a 300 megaparsec scale, the RMS density fluctuations would be about 3.2%. And also, this should be what you're seeing with the galaxies because the KBC results probe the vast majority of the luminosity function. They probe more than 57% of it.
When you observe very massive galaxies, they're biased with respect to the dark matter.
Yeah, that's right. The bias issue is one of the most important things, but we're not observing only the most massive galaxies.
I think that's what I was just starting to realize,
In the KBC paper, they explicitly demonstrate how much of the luminosity function they're actually able to probe. And the result is somewhere between 57 and 75%, which should be enough to know basically the total normalization of the luminosity function in different redshift regions. So the RMS density fluctuations should be about 3.2%. The observed underdensity is 46%, plus minus 6. So this is obviously much larger. So on here, we plotted in blue the underdensity, so just a histogram of that. And there's an allowance for the redshift space distortion effect of the underdensity affecting the velocity field. The red line is just the 46 plus minus 6% figure that's been reported by observers. So you can see there's a very serious mismatch here. The KBC void, therefore, falsifies ΛCDM at 6.04 sigma.
Do you want to maybe quickly unpack what this redshift space distortion effect is?
The redshift space distortion arises because if there is actually an underdensity of, say, 10%, then there must be outflow from some central region in order to create this underdensity. And that will then distort the relation between redshifts and distances. So the Keenan-Barger and Cowie used a fixed distance redshift relation where they assumed the Hubble constant of 70 kilometers a second a megaparsec. But in reality, the amount of volume corresponding to some range of redshift, it would be different to what they assumed. And actually, this has the effect of broadening the distribution slightly, because the apparent underdensity would have a dispersion of 4.8% instead of 3.2% if you apply this RST correction. But that is included in this. This RST effect, by the way, is slightly larger also in the MOND case, which we'll come on to later. One of the important results then is the KBC void falsifies lambda CDM at slightly over 6 sigma. Relating to your question about the redshift space distortion, this is actually a very critical part of the whole talk, because the redshift space distortion is obviously related to the impact that the void has on the locally measured Hubble constant, which is what I was going to come on to next. So what's shown on this graph is the apparent underdensity on the y-axis, and on the x-axis is the ratio between the locally measured Hubble constant and the background or global value. In lambda CDM, you expect to measure this green dot. So there is no underdensity and the local Hubble constant is equal to the global value. This is on average the expectation in lambda CDM. But you have cosmic variance, and with cosmic variance, you can have a small underdensity, or you can have at the 5 sigma limit or a 25% apparent underdensity. And this will have a small impact on the Hubble constant. The important thing is that the observations and their error ellipse is shown here. So the observations indicate a much deeper underdensity and a much larger Hubble constant locally than is expected in lambda CDM. The 5 sigma limit that you can reach in lambda CDM, even allowing for cosmic variance, is not enough to get within the 5 sigma error ellipse as defined by local observations, indicating an extremely serious problem altogether.
Can I just ask a quick, slightly stupid question? So the red dot is labeled as Rees et al. And Wang et al., but the delta value of the red dot is this KBC measurement, right?
Yes. The formal significance of this is 7.09 sigma. One reason why it's so high is because the axes are measured in independent ways. So, for example, a error in the calibration of type 1a supernovae, which sort of multiplies all the H0 values by 1.05, for example, would obviously affect the x-axis, but it would not impact on the underdensity measurements of Keenan, Barger, and Cowie, because it would simply cause the densities between 40 and 300 megaparsec to be multiplied by some factor, but exactly the same factor would apply further out. And therefore, the relative density contrast would stay the same. It would still be 46%. So the independence of these axes is important, which means that the KBC void and Hubble tension independently falsify lambda CDM at more than 5 sigma. So it's an extremely serious problem. The implications are quite far-reaching. Essentially, what this proves is that you cannot get from the boundary conditions of the CMB at z equals 1100 to the actually observed nearby universe at z equals 0 or within 0.2. This problem is on a 300 megaparsec scale, so it's independent of galaxy scale baryonic physics. The only way this enters is through this abundance matching prescription, which essentially lambda CDM has to kind of work like that, if it's correct at all. Now, this means that you need effectively stronger gravity in order to grow structures more efficiently than in lambda CDM, assuming that the CMB boundary conditions are what they are. So this is essentially what we were exploring. Now, the other main motivation for us, in addition to these observations, was the constraints from data on galaxy scales. So this is basically a typical rotation curve of a galaxy. You can see the measurements up there. And what's shown here is the expected rotation curve from the baryons alone, if you use Newtonian gravity. There is obviously a huge mismatch here, which is the well-known flat rotation curve problem. Now, this discrepancy also is evident here. So on this graph, we've shown instead the observed acceleration or the centripetal acceleration, just the v squared over r, against the expected acceleration from the baryons, assuming Newtonian gravity. What should happen ideally is that they would be the same, in which case it would follow the line of equality. Of course, they do not. The actual data lie much above it. The important thing to realize about this graph is that although the 20 or so points from this galaxy are shown on here, there's many other galaxies shown on here as well. There's 153 galaxies altogether that are shown on here, contributing nearly 2,700 data points. And you cannot distinguish the galaxies on this graph. They all trace the same relation. So some will probe only this part and some only this part, but they're all on the same relation. And the residuals about it are quite small. In fact, there is some dispersion evident about the relation, but this can be assigned to measurement errors alone. So this looks like a fundamental relation.
And are the red dots just an average?
Yes. Now, this brings me on to the idea of Milgromian dynamics, or MOND, which essentially just fits the red dot, so to speak. The reason this is an interesting idea is that Newtonian gravity and even general relativity were developed using solar system constraints more than 100 years ago. Importantly, they also did not account for quantum mechanics, which I'll come on to in a sec. But the main empirical constraints were then potentially very seriously out of date. The addition of more recent data from galaxy rotation curves, such as what you saw in the previous slide, led Mordechai and Milgrom in 1983 to try and address the actual observations of galaxy rotation curves without assuming cold dark matter by going beyond Newtonian gravity. So this is possible using a Lagrangian formalism, which is actually similar to some quark confinement theories. In this Lagrangian, the kinetic part is standard, but the gravitational part is non-standard. If you extremize the action using the Euler-Lagrange principle, you therefore get the standard equations of motion, but the gravitational field is very different for the same baryonic distribution than in standard theory. Importantly, there's this nu function, which is the critical thing. Gn is the Newtonian gravity and G is the actual gravity. Now, because nu is a nonlinear function of the Newtonian gravity, this theory breaks the strong equivalence principle, leading to the external field effect, which we'll discuss in more detail later on. The main thing is that's just a consequence of having a nonlinear theory. The parameter A0 that is needed to make this work is about 10 to the minus 10 meters per second squared, which is related to the first point, much less than anything you probe in the solar system, about 4 orders of magnitude less. Before I try and justify this value of A0, I just want to briefly recap the basic behavior of the MOND theory in spherical symmetry, which is that at high accelerations, the gravity is the same as the Newtonian gravity. And at low accelerations, the gravity goes as a square root of the Newtonian gravity, which causes the point mass gravity law to be inverse distance, leading to the flat rotation curves you saw on the previous slide. Regarding the justification for this particular value of A0, this is not currently possible to derive exactly from a deeper principle, but one very interesting coincidence is that if you do not look at galaxies, but you look on a much larger scale, you notice this accelerating expansion to the universe, which is often ascribed to dark energy with some density rho lambda. Now, if you have a gravitational field, then every sort of volume of space-time has some energy density in it due to the gravitational field. This is related to the square of the gravitational field strength. Now, this energy density in the gravitational field becomes very small if the G is very small. And in some circumstances, it is even less than the energy density carried by the dark energy. The importance of this is that the dark energy density is often thought to be a 0-point energy of space-time due to all the quantum fields, which cannot be exactly 0. As a result, it's entirely possible that there would be quantum corrections to the behavior of gravity in some regimes. In particular, if this inequality is satisfied, we might expect quantum corrections to be quite significant. Now, coincidentally, that also would imply that the G is less than about 2 pi times A0. It's not exactly correct, but there is certainly an order of magnitude agreement between the gravity implied by this equation, which has nothing to do with the dynamics of galaxies, and this A0, which is obtained from galaxies. So yeah, there's certainly concepts on here which are not currently understood, that's for sure. But this is trying to show why it might be a plausible thing. Now, returning to somewhat less speculative matters is that we do have a relativistic MOND theory in which gravitational waves travel at the speed of light. This was published last year by Scordis and Zlotnik. So this is actually a problem for a lot of other alternative gravity theories to do such a thing. It's possible in MOND. One often raised objection to the MOND framework is how it is supposed to relate to cosmology. So you've seen that it can explain galaxies fairly well, but it should be able to explain other things as well, of course. So obviously in this paper, we had to make some assumptions regarding how MOND would work in a cosmological context. What we used is this new HDM framework. This HDM stands for the hot dark matter. This was proposed by Gary Angus in 2009. So we haven't actually invented this new HDM framework. This was invented for various reasons, which we'll describe as we go along. So the basic picture is that this cold dark matter chunk of the cosmic pie is replaced by some form of collisionless matter, which we're assuming is sterile neutrinos with a mass of 11 electron volts by c squared. The main reason is that if these sterile neutrinos were thermalized, then they would have the same total density as the CDM in lambda CDM. So this mass is not arbitrary. The overall cosmic pie chart then stays the same. This leads to a standard background cosmology or expansion history, because the MOND version of the Friedmann equation is obviously different to the classical one. However, the differences are very, very small. So you essentially have a standard Friedmann equation, a standard background cosmology, which also leads to standard Big Bang nucleosynthesis. So the primordial abundances of deuterium and helium should be the same. Not exactly, there's some slight difference, but it's again very small. There is obviously a difference between the new HDM and the lambda CDM frameworks. And this arises because MOND gravity rather than Newtonian gravity is applied to the density perturbations.
And that's because the dark matter is hot and so therefore it doesn't fall into the density perturbations?
No, it does. I mean, you have to, when I say the perturbations in both the baryons and the dark matter. It depends which scale you are looking at. I'm going to explain in more detail on which scales the dark matter would cluster and which not, and this is important. The other thing is, if you applied MOND gravity, then because of the nonlinearity of MOND, that would automatically lead to the external field effect, which will just arise automatically in a self-consistent simulation. If you want to read more about how this works without doing a simulation, just using pen and paper, then you can look at this link. Now, in this new HDM framework, one important aspect is the causing microwave background radiation. Because we have a standard expansion history, the angular diameter distance to the CMB is the same. Now, what I'm going to argue next is that the actual physics of the early universe, the plasma physics, should also be the same. So there's a couple of reasons for that. One of them is that the gravitational fields are about 20 A0, meaning that the problem is still in the Newtonian regime. So MOND does not change the gravity at that epoch.
Is there not even like a 1 in 20 sized effect?
Well, you can change the interpolating function to make it an exponential cutoff.
So there'd be an e to the power of minus 20 sized effect.
Yeah, you can make it e to the minus 20 rather than 1 over 20, because this is much above rotation curves typically probe, and therefore they don't tell you that there's a 5% change at 20 A0, for example. The other reason why this new HDM framework does not impact the CMB very much, the physics of the CMB, is that the free streaming of the sterile neutrino is not very significant. So according to the Planck collaboration 13 paper, if the sterile neutrino mass is more than 10 eV by c squared, then they've stated explicitly that the particles are so massive that their effect on the CMB spectra is identical to CDM. So anything above 10 eV by c squared is fine. So obviously 11 would be fine. Now, what is shown here is the CMB power spectrum in ΛCDM in red and in blue in the nHDM framework with 11 EV by c squared sterile neutrinos. The differences are very, very small and can't really be distinguished. There's also some adjustments that can be made to the cosmological parameters, obviously, like to a very small extent to try and remove any residual differences. As the universe is expanding, however, the gravitational fields become weaker, and below redshift of 50, then MOND is important. So it does affect the formation of the first galaxies, for example, which might have happened around redshift 20. And then at late times, in the late universe, it's obviously important. So that's a basic picture regarding the CMB and essentially the early universe.
This is a 2011 paper, so Planck wasn't around yet.
But this one is from 2016, though.
The text is, sure.
Yeah, we should actually revisit what the spectrum would look like with the latest data. That is true.
Because one of the things I found quite interesting is that the sterile neutrino has actually also got a bigger value of H. It's got 0.73 instead of 0.71. So, I mean, I don't think this is going to solve the Hubble tension without the new as well, but it could be that including hot dark matter changes Planck's best fit H0 from 0.67 to 0.69 or something like that.
It could well change. Yeah, exactly. The best fitting parameter values are likely to change somewhat.
Yeah.
Yeah, you're right. I don't think it will solve the problem because the peak position is very well measured, and that is essentially what tells you H0.
The other thing I was thinking is there are these other funny things going on in the CMB, like the lensing in the tail of the thing being slightly larger than ΛCDM would predict. And they fit it with this A lens parameter. If Angus and Diaferio in 2011 are the cutting edge of this, then I guess one needs to update this for 2020. But I was wondering whether if one included a 1/20 effect or a 1/200 effect coming from MOND, maybe that is actually potentially able to explain these funny things in the CMB as well.
It could do. The other thing that could happen is that because MOND also would enhance structure formation, that could increase the amplitude of the foreground lensing of the CMB. But these things would require a larger simulation to address the things like the iterated Sachs-Wolf effect. By the way, the issue you raised regarding the A-lens, that we did mention that in the paper, and we did mention also a few other evidences in the paper that the CMB might be lensed more by foreground structure than expected in ΛCDM, because there are some other evidences for that as well. Right, so yeah, this is essentially all I wanted to say regarding the early universe in the MOND nHDM framework. The sterile neutrinos is obviously one aspect to this model. There is also some independent evidence from terrestrial experiments for these sterile neutrinos. They've been proposed to explain why the ordinary neutrinos have mass, which is by now well established. One possibility is this seesaw mechanism. In addition, there are actually hints of a sterile neutrino in some studies. Now, what we've shown here is from this paper, the probability of a sterile neutrino actually existing with particular mass. That's shown in orange. And you can see that there is actually like potentially an additional sterile neutrino. It would help explain certain observations. The main problem is that the graph has been cut off at 10 EV by c squared. The reason for that is this blue line, which is the cosmology constraint. And that tells you that you shouldn't have a high mass sterile neutrino, but this is assuming ΛCDM. So obviously in nHDM, this blue line would not appear there.
Where is that coming from in ΛCDM?
In ΛCDM, well, I think if you had such high mass sterile neutrinos, then there would be no cold dark matter left to explain galaxies.
Ah, I see. So this would be very subdominant dark matter. I see. And there'd be another cold dark matter somewhere else in particle physics land.
Must be. In ΛCDM, there must be. So this brings me on to the slightly smaller scale issues. These sterile neutrinos are important to explain observations such as the bullet cluster, where we see an offset between the X-ray peak in red and the weak lensing peak in blue. So this is often considered strong evidence for collisionless matter. In the nHDM paradigm, this is not disputed. It is considered evidence for collisionless matter, but it's important to understand just what kind of collisionless matter could explain these observations. The first thing to understand is that it's difficult to explain this just through the fact that MOND gravity is different to GR, because the gravitational fields are stronger than A0. And therefore, this is basically still standard gravity, which means that we probably do need collisionless matter in the Bullard cluster.
Normally, MOND is becoming relevant within galaxies. Presumably, a galaxy cluster is much, much larger, and when you're far away from the center of it, the gravity's weaker, or is it so much more massive that the gravity's still stronger?
In galaxy clusters are typically in the regime where you're at sort of 2 or 3 A0.
Okay, I have a really, really stupid question now then. If I'm in a galaxy that's inside a galaxy cluster, it can't be literally just the magnitude of the gravitational field that matters for MOND.
No, the absolute magnitude does matter. So indeed, that is an important question. If you have a disk galaxy inside a galaxy cluster, then the external field of the cluster would significantly affect the internal dynamics of the galaxy. Whether this is correct observationally or not is currently being investigated. In fact, I'll come on to at the end some strong evidence for this external field effect.
I understand this point on the slide then. Because it's a galaxy cluster, the gravitational field is much, much stronger, and therefore MOND effect should be small.
Which still leaves us to explain the observation somehow. The most logical way is that there is some collisionless matter. Now, if you try and explain that with sterile neutrinos, because of the fact that they're fermions, there's some Tremaine gun limit. The number density cannot be arbitrarily large. Essentially, it's the Pauli exclusion principle. Now, because we know how much mass density is required to explain the weak lensing peak, that imposes a lower limit to the mass of the sterile neutrino. However, this lower limit is about 2 eV by c squared. So in principle, anything more than that would explain the Bullard cluster. Perhaps not everything else. In order to explain other galaxy clusters, I think sometimes they need slightly higher values. But 11 would in all cases be fine. That was explained in a previous paper by Angus. So the current constraints, if you look at all the different galaxy clusters, including systems which are more virialized or spherical and perhaps a bit easy to analyze, and also if you look at the CMB, including with the Planck data, then putting it all together, you need a particle with a mass greater than 10 eV by c squared. But again, 11 obviously would be fine. So that's the nHDM paradigm.
Within ΛCDM, there's a kind of isn't there question about whether the bullet cluster is colliding too quickly? Like it kind of depends on measurement errors, and it may not be intention in ΛCDM. So I was going to wonder, does MOND, when the galaxy clusters are apart, maybe the force between them, maybe...
We're doing a study on the bullet cluster and on El Gordo, and I don't want to explain exactly what the results were just now, if that's okay. But it'll be published very soon. Just to recap this nHDM framework, because it has a standard matter content or pie chart to the whole, what the universe contains, it yields a standard sort of expansion history, which can explain the primordial abundances of light elements. It can explain the CMB because the gravitational fields are strong then, and because free streaming effects are currently not detectable for an 11 eV by c squared sterile neutrino mass. It can explain the bullet cluster. It can explain galaxy rotation curves. Now, this is important. If the sterile neutrinos have a mass less than about 100 eV by c squared, then galaxies contain too little sterile neutrinos for their rotation curves to be much affected. They are nonetheless affected by MOND. So this means that galaxy rotation curves are explained using MOND, which solves actually a lot of problems with ΛCDM on the dwarf and galaxy scales. So for example, one of the most serious is the plane of satellites around the Milky Way, which have high internal velocity dispersions. These are probably tidal dwarf galaxies to explain why they lie in a thin plane. But if they were actually tidal dwarfs, they shouldn't have any dark matter. So the high internal velocity dispersion is then suggestive of enhancement to gravity, because it can't really be explained by dark matter. This problem, by the way, is not restricted to the Milky Way. It also rises around Andromeda and Centaurus A. So the only 3 galaxies where we can see the 3D distribution of satellites. So there's no question of a look elsewhere effect. We can't look elsewhere except these 3 galaxies for now. The ΛCDM community have suggested a lot of explanations for the satellite planes, but none of them work. So this is a very detailed study explaining exactly why that is. Then there's various other small scale serious problems for ΛCDM, such as the high prevalence of thin bulgeless disk galaxies, which is unexpected if galaxies have huge dark matter halos and are merging quite often. There's some other problems have been discussed also. Okay, so with that, I've explained how the nHDM handles the early universe. and rotation curves and galaxy clusters. We haven't applied it to the KBC void. This is what Moritz is going to do next.
Okay, I will now explain our cosmological MOND simulations and the results of these simulations. So we set up now this cosmological MOND simulation, which involves the density contrast starting from redshift 9 up to present time, and motivated by the observation from Karantsev, we assumed an initial Maxwell-Boltzmann under-density profile with an amplitude consistent with the CMB. As Indranil already explained, this model has a standard expansion history because of the overall mass budget, and following also other structure formation simulations in MOND, we applied MOND only to the density perturbations. And the void as a whole is moving because of the external field effect from large-scale structures beyond the void.
Amplitude consistent with CMB, does that mean it's like a 1 sigma typical fluctuation or 2 sigma or?
So when you scale the density IMS fluctuation from redshift 1100 to about redshift 10, then for the lambda CDM, you would expect a density IMS fluctuation about 10 to the minus of 2. And so we set a range from 10 to the power of minus 5 to 10 to the power of minus 2. This external fields from the large-scale structures, which are beyond the void, affects the velocity field of the void. And I will come to this in more detail later. So this is the first result of our best fitting model. And this plot here shows the time evolution of the density contrast for a sphere with a co-moving radius of 300 megaparsec in a MOND and in a lambda CDM simulation. So when we compare now the red solid line, which refers to the lambda CDM model, with the blue solid line, which refers to our best fitting MOND model, we can see that the enhanced growth of structure in Milgromian dynamic leads to a much deeper void than in an Einsteinian Newtonian gravity. And we also run now as other MOND version in which we have a time-independent external field effect. In this particular model, which is this blue dashed line, we have a model where at present time we have the same external field effect as in our best fitting model, but we have a much higher external field effect in the past. And external field effect makes a system more Newtonian. This means that I need also a larger initial density fluctuation in the past in order to get KBC-like voids at present. And this is shown in this plot.
Is the solid one the more realistic one, or is it that we just don't know the size of the external field effect?
The solid one is, so to say, the simplest one because it assumes that it's time independent, but I think it's more realistic having a time dependent external field effect. So now we show here the radial density profile of the KBC void in our best fitting model. So what we can see here on the x-axis is the co-moving radius in megaparsec and the density contrast on the y-axis. And this dashed line here is the redshift space distortion corrected density contrast of the inner part of the KBC void between 40 and 300 megaparsec. And the other one is the ISD corrected value of the KBC void between 600 and 800 megaparsec. And this brown line here refers to the density profile when the universe was 0.7 gigayears old. And now I evolved this over time. So time is running and the density contrast increases. And at present time, when the universe is 13.8 gigayears old, we can match the observations by KBC in the inner part roughly at the 1 sigma level and at the outer part roughly at the 1 sigma level. This is the model at present is this blue line. Now I come maybe to the most interesting result of our simulations. As explained at the very beginning, an under-density affects the cosmological parameters in the local universe because parts of the universe beyond the void with more galaxies pulls galaxies in the void outwards. And this causes that the local expansion rate is increased And has another effect, the apparent expansion rate appears to accelerate at late times, which is the so-called acceleration parameter. And this describes an extra curvature of Q0 power of the Hubble diagram. Now, looking at the observations, Camarena and Mara in 2020 jointly derived now H0 and Q0 power from supernova data at redshifts between 0.023 to 0.15. And what is very interesting here is that their acceleration parameter is 2 times larger than the standard value, which is predicted by the ΛCDM model, which is 0.55. And this is a hint that this is driven by a local void because it gives you an extra curvature in the Hubble diagram. Now, there was in 2019 a study by Kenworthy et al., and they concluded that based on local supernova data, a huge local underdensity is excluded by 4 to 5 sigma. But in their analysis, they used a fixed Q0 bar at 0.55, which are the Planck predictions, and so they do not allow an extra curvature in the Hubble diagram. What we can see here now is on the x-axis, the Hubble constant, and the acceleration parameter on the y-axis, and the green dot is from the Planck collaboration. And now I overplot the observations by Camarena and Mara 2020. This is this black dot here, and with the 1 and 2 sigma counterlines and the 4.39 sigma counterline, which tells you that there's a discrepancy between the Planck collaboration and the observations of 4.4 sigma. And now I plot the results of our best fitting MOND simulation, and our models can explain the local observations by Camarena and Mara at the 0.2 sigma confidence level. You can see this with this blue star. Now, in order to test the robustness of these results, we also run models with a different initial density void profile, namely a Gaussian distribution and an exponential void distribution. And here we get that these profiles can explain the local observations also within the 1 sigma level. You can see it here, and both data points overlap here because they give us almost the same value. So this data point refers to the Gaussian and to the exponential profile. And therefore the high local H0 and the acceleration parameter are explained naturally in MOND by KBC like voids.
Can I just check something? This star is when you use the MOND physics to generate the KBC void. And then once you've done that, you will get this value of H0 and this value of Q0. It's not so much a prediction that MOND will produce this value of H0 and this value of Q0. It's a prediction that MOND plus us living in the KBC like void would generate this.
Yes, if we are not in an underdensity, for example, so if the density contrast is exactly the cosmic mean, then we would obtain the Planck values. Okay, now I come to the peculiar velocity field of the void, which is plotted here. Where the mouse is pointing is the center of the void, and we only show here half of the void IMS size because observations imply that we are very close to the void center. So we show only half of the IMS size here. So here is the center of the void, and the color index shows the total peculiar velocity in the CMB rest frame. Now, as explained previous, the entire void is moving due to gravity from beyond the void. And in our best fitting model, the entire void is moving with 1,586 kilometers per second. There is now a partial cancellation between the void motion and the internal velocities, which gives us now regions which have a total peculiar velocity lower than this 1,586 kilometers per second. And the local group is moving with 627 kilometers per second with respect to the CMB. And this line, which highlights this 627 kilometers per second, is this black line here. And we expect that the local group is centered at this black line. because this is the line with the 627 kilometer per second, and we indicate this with this yellow star here. And here you can see that the local group is off-centered, so it's not in the middle of the KBC void, and we are not at the special position at the void, because we quantified that this region causes a 2.34 sigma tension, and we come to this in more detail later then. So from this we can conclude that the local group is not at a special position here. And high peculiar velocities towards the void H is consistent with the kinematic Sunyaev-Seldovich effect. So we get here at the H here, where mouse is, very high total peculiar velocities of about 4,000 kilometers per second. So this is a very unique expectation from our model. And this brings me now to a comparison of the ΛCDM model and the nHDM model. So starting with the ΛCDM model, using the Millennium XXL simulation, the KBC void falsifies ΛCDM with 6.04 sigma. And recently, combining the results from Rees et al. 2019 and Wong et al. 2020, the H0 tension reached the 5.3 sigma level. When we combine this, and given that the parameters are fixed by this at the CMB, this gives us a combined tension of 7.09 sigma, as Indranil explained at the first part of the presentation already. Now, looking at the nHDM model, we have here now 12 observational constraints. So as explained, the inner part of the KBC void gives roughly a 1 sigma level tension. The outer part of the KBC void gives roughly a 1 sigma tension. H0 and Q0 bar from local supernova data give a 0.2 sigma tension. Then we also constrained our models from H0 derived from 7 strong lens time delays. This gave us a 2.05 sigma. And from the last slide, the motion of the local group gave us a 2.34 sigma. So we have in total 12 data points here and three free parameters, namely the void size and strange and the external field strange. And this gave us then a combined tension of 2.53 sigma, which is a significant improvement compared to the ΛCDM model.
Can I just ask a quick question about this strong lensing time delay? I guess that's also the Wong plus 2020 in the ΛCDM.
Yes.
So Wong was this holy cow group, and then they've become TD Cosmo. And TD Cosmo released a paper about 3 or 4 months ago, kind of reanalyzing all of their stuff. And their error bars have substantially increased, and their value of H0 has actually dropped quite a lot to be more consistent with Planck. The Rees et al. One is still just as inconsistent. So the ΛCDM tension might go from 7.09 sigma to 6.6 or something. It's not going to change your conclusion whatsoever. But I wonder whether this your H0 from 7 strong lensing time delays, if you were to reanalyze it with the more modern TD Cosmo instead of holy cow, it might give a slightly different number. That would be interesting to look at.
And now this brings me already to the summary and conclusion slides. So using the Millennium XXL simulation, the KBC void falsifies the ΛCDM at the 6 sigma level. And given that the Hubble tension falsified ΛCDM or reached the 5.3 sigma level, the combined tension using KBC void and the Hubble tension give us a 7 sigma tension. And the implications are far-reaching because the failures of ΛCDM covers now all scales ranging from dwarf galaxies to gigaparsec scales. And the meta distribution on a gigaparsec scale is observed by Keenan et al. Tells us a strong indication for enhanced growth of structure, which can be achieved with Milgromian gravitation. So therefore we set up a MOND cosmology with fast collisionless matter. So for example, this could be 11 electron per c² sterile neutrinos. And this model was proposed by Angus in 2009. This model has an almost standard expansion history, BBN and CMB anisotropies. The structure growth is enhanced, and we have not discussed this here in much detail, but in our paper, there's a self-regulation effect by external fields from surrounding structures. And the MOND model describes the local observations at the 2.53 sigma level. And the enhanced growth of structure allows the formation of the KBC-like voids, and the locally high measured Hubble constant and acceleration parameter are just in MOND a logical consequence because of this enhanced growth of structure. And therefore, thank you very much for your attention.
So where will you be going to next? What are the new things that need to be done on this topic?
So in the next step, it is important to study galaxy formation and evolution in a cosmological context, for example, by using the phantom patch to the standard Ramses code. And this is currently done by the PhD student Niels Wittenberg, who is also a PhD student in the Stellar Populations and Dynamics Research Group led by Professor Pavel Krupa. And I can show some preliminary results of his simulations. This movie shows the evolution of the density contrast in Milgromian dynamics. And the simulation has a box length of 15 megaparsec. And the simulation has been performed by Niels Wittenberg and Indranil. So here you see the density contrast now at present time. You can nicely see the cosmic web and the voids which have these darker regions. And this is important to have a self-consistent cosmological MOND simulation on much larger scales, because this would allow us then to study the formation of voids in a large simulation box, and also to get an idea how the KBC-like void profile will look like, and also to study the cosmic variance on different scales. And another point is that the community should be more open-minded towards models beyond ΛCDM. And we should also have in mind that if one particular model can explain the data, it does not imply that the data cannot be explained by another model. Like, for example, here the CMB, as discussed by Indranil before.
If the KBC void exists and is this extreme and can't be predicted by ΛCDM and can be explained by nHDM, surely we should also see a lot of other equally extreme things. People who do void studies for a living do things like find voids in the large-scale structure, measure their ISW effect, measure their redshift space distortion effect, and it doesn't seem like they're getting massive conflicts with ΛCDM. Are they just not analyzing the data in such a way that they'll see how it's inconsistent with ΛCDM, or is there something else going on there?
Yeah, this is actually a very important question regarding other anomalies in large-scale structure. In our paper, we do discuss certain other anomalies. So regarding the galaxy clusters, we are actually currently working on an article that shows that this also seems to be incompatible with ΛCDM. But regarding the integrated Sachs-Wolf effect, there was a paper that we've mentioned by Kovacs that this seems to be 5 times stronger than in ΛCDM. Now the error bars are still somewhat large, but yeah, it's certainly not incompatible with significantly more structure than expected.
So yeah, the last question of both of you, what do you think is the most interesting thing in cosmology at the moment?
One of the most interesting things, in my opinion, is related to this external field effect. And that is this recent paper which claims to have detected the external field effect at very high significance based on the rotation curves of galaxies in environments with a weak or a strong external field based on the surrounding galaxies. So first of all, if I show what happens to the galaxies in more isolated environments, if you do the rotation curve fits with the EFE or without the EFE, the external field effect allowed in the analysis, it doesn't make much difference. So allowing the external field effect in the fits does not substantially help the fit, which you can quantify with the Bayesian information criterion. There is obviously some improvement with the EFE, but it's not enough to justify the extra parameter. Now, looking to the more interesting case of galaxies where there is supposed to be a strong external field effect based on what is around them, here, there is very strong evidence for the EFE just looking at the rotation curves. This is apparent in that if you don't have the EFE, it's not possible to match the data properly. But if you include it, then you can get a very good match. The Bayesian information criterion, if it's more than 10, then there is very strong evidence for this extra parameter. The actual values are, in this case, 84 and 144. So in this paper, it says that the formal significance of the detection is between 8 and 11 standard deviations, depending how it's measured. And this has recently been accepted for publication in APJ. Also, the other thing is the value of the external field that's inferred from just looking at the rotation curve is consistent with prior estimates based on the surroundings of the galaxy in question.
Interesting. Is that the difference between this E environment and just E?
Yes, so the EN is the prior expectation from the environment, and the E is what is inferred by the MCMC looking just at this galaxy. It's not just with these two galaxies. They analyze the entirety of the spark sample of 153 galaxies. And obviously, there's a continuum between galaxies which are strongly affected by the EFE and ones which are not.
Definitely something for the viewers to check out. And Moritz, do you have an idea of the most interesting thing in cosmology outside of your own research?
I would be interested by what extent the CMB is contaminated by foreground dust. We briefly discussed this in our paper. Like, for example, there's a paper by Warwichuk in 2018, and he proposed a model in which the entire CMB is thermal radiation from intergalactic dust particles heated up by starlight. And I would be interested if this is a viable model. But even if not the entire CMB is dust, it might significantly affect also other cosmological parameters. And I would be interested to what extent this will be the case.
One would wonder how, if it was thermal dust emission, how on earth it mimics sound waves in a primordial plasma. But I guess he must have thought about that. But that would be my initial extreme skepticism. But certainly as a subdominant contribution, that doesn't seem immediately and obviously ruled out. Thank you everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified whenever there's a new video, and click like to help with the YouTube algorithms, and share the channel and this video with your colleagues. If you have any questions of Indranil and Moritz or any suggestions, please leave a comment. While you're here, you can watch another video. This recent work by TD Cosmo came up. We actually had Simon Birrer, who was the lead author on that work, on the channel a few months ago. So I'll put a link to that video. You should be seeing it right now. And thanks again, Moritz and Indranil, for the great talk.
Thank you.